Good morning, students. Today we will solve one problem on gas turbines. Now, this problem is taken from one of the semester examinations conducted by MACAUT on the subject thermal power engineering in the year 2018-19. The problem statement is as follows. A simple gas turbine takes air at 1.01 bar and 15.5 degrees centigrade and compresses it through a pressure ratio of 5:1. The adiabatic efficiency of the compressor being 85%, the gases enter the turbine at a temperature of 540 degrees centigrade and expand to 1.01 bar. The turbine efficiency being 0.8. Estimate the flow of air and gases in kg per second for a net power output of 1500 kilowatt, making the following assumptions. Fall of pressure through the combustion system is 0.07 bar. Cp for both air and combustion gases are 1.047 kilojoule per kg Kelvin. K is equal to 1.4. Now let us see the solution. Now the problem statement is rewritten here. Now we see that the values which are given are colored with green and the quantity that is to be determined is colored with red. Okay. Now let us follow what are the properties that are given. So initial condition is given, you see, 1.01 bar and 15.5 degrees centigrade, these are given. So initial temperature that is 15.5 degrees centigrade. So here initial pressure and initial temperature given. So here you see that initial temperature 15.5 degrees centigrade and the initial pressure P1 is equal to 1.01 bar is given. So 1 is the initial condition or that is the initial state in the gas turbine system. So then the pressure ratio is 5:1. So as we know that in a gas turbine, there will be basically in the stage, there will be a pressure change. So from this value that is at the initial state to that after compression state, there will be a change in pressure. So due to the compression, that means this pressure ratio is across the compression. So 1 to 2, there will be a pressure increase. So that is 5:1. That means P2 by P1 is basically 5:1. The adiabatic efficiency, that is the isentropic efficiency of the compressor, is given as 85%, and that of the turbine is given as 0.8. Okay. Next, the turbine inlet temperature is given 540 degrees centigrade. So this is the inlet to the turbine, that is 540 degrees centigrade. That is also the maximum temperature in the cycle. So this is 540 degrees centigrade. And turbine exit pressure is again 1.01 bar, so that it is the same pressure from 4 to 1. Now we have to determine the mass flow rate for which the total power output will be 1500 kilowatt. So mass flow rate of the air or the gas we have to determine. Now there is one assumption that the fall of pressure through the combustion system or the combustion chamber is given as 0.07 bar. Now here one thing we have to understand that this is now here we have drawn the ideal cycle as well as the actual cycle. The ideal cycle is drawn with red color. Thick red lines are representing the ideal cycle and corresponding a little thinner and dashed lines with blue color, light blue color is representing the actual cycle. Now here you see that for this process 1 to 2 there is a deviation because the compressor has some isentropic efficiency, so there is a deviation. Again, in the turbine also there is a deviation. Now the thing is that in the combustion chamber also it is told that there is a pressure fall. So that pressure fall means this is no more a constant pressure process. There is a pressure fall from 2A to 3A. Now A means basically it is the actual state and S means corresponding to the isentropic state, isentropic process. That means from 1 to 2, if the process is isentropic, it is 2S. If the process is actual, it is 2A. Now, from 2A, there will be a process up to 3A in the combustion chamber due to the decrease in pressure. Now, from that 3A, that is the turbine uh, inlet condition. Now, that we have to consider that 3A, that is the temperature here. Actually, that is the maximum temperature, 540. So this is corresponding to 3A, not 3. Okay, here it is little, or it can be like, it can be extended up to that maximum temperature and from that it will fall. Anyway, now we have tried to draw both the cycles, that is the ideal cycle and the actual cycle. Now, there will be a process from 3A up to 4A in the turbine, actual turbine process. And from 4A, it will be completing up to 1, state 1. Now, the other values are given, Cp value and the corresponding isentropic index or the specific ratio values are given. So in both the cycle, in both the diagrams, that is the PV diagram and TS diagram, we have tried to show the cycle. So in both of these diagrams or both of these thermodynamic planes, the red line is showing the ideal cycle and the light blue color line is showing the actual cycle. So there are deviations from the theoretical or the ideal cycle. All the values are mentioned. Another thing is that this is inlet pressure and there is a pressure drop from the value of 2 up to 3. So there is a pressure change, that is 0.07 bar. So this is the pressure fall from 2 up to 3A. Okay, as usual, these are isentropic processes in case of ideal cycle, and these are constant pressure process. This is no more a constant pressure from 2 to 3A, but this is a constant pressure as it is mentioned that in the turbine exit, the pressure is same as the inlet pressure. Both are 1.01 bar. Okay. Now, the given data, P1 is given as 1.01 bar and T1 is equal to 15.05 degree centigrade. So accordingly converted in Kelvin to 288.65 Kelvin. Now P2 by P1 is 5 by 1. Therefore, P1 given, so we can determine P2. P2 is equal to 5 P1 and therefore it is 5.05 bar. Next, we will look into the definitions of isentropic efficiency to calculate other temperature values from the given value of the temperature as well as the isentropic efficiencies. So isentropic efficiency of the compressor, that is the theoretical or the isentropic work input divided by the actual work input. Now that is from the definition, and accordingly for this the change in the enthalpy multiplied by Cp. So Cp values are same, therefore we have cancelled already, and it is in terms of the enthalpy. Since work can be represented from the work can be expressed from the first law in terms of the enthalpy change. So during the compression process, that is the theoretical process, it is 1 to 2s, and in case of the actual process, it is 1 to 2a. So accordingly, it is 1 to uh, the mass flow rate. I did not write because mass flow rate are same, so it is already cancelled. And so it is H2S minus H1 for the theoretical or ideal, and for the actual it is H2 minus H2A minus 1. So that is coming from the first law. Now writing in terms of Cp delta T for ideal gas. So it is Cp delta T for the theoretical process and Cp delta T for the actual process. And this is given as 0.85. That is the efficiency is given as this. So here you see that T1. Now we will write the definition of the isentropic efficiency of the turbine. In the same way, turbine isentropic efficiency, it is simply opposite of that of the compressor. So it is Wt actual by Wt theoretical or isentropic. Now this is in written in terms of enthalpy change. Mass flow rate already cancelled because they are same. Now H3A minus H4A, you see that there is H3. Now it is the starting point, and it is going from this up to 4s in case of isentropic process, and from 3a up to 4a for the actual process. So actual means from 3a to 4a, 3a to 4a, and for the theoretical it is 3a to 4s. Therefore, it is 3a to 4s, and accordingly written in terms of Cp delta T for the ideal gas corresponding temperature value. So it is T3a minus T4a divided by T3a minus T4s, and the value for the isentropic efficiency of the turbine is given as 0.8. Now, you see, it is mentioned that there is a pressure drop in the combustion chamber during the process from 2 to 3. So in during this process 2 to 3, there is a pressure drop due to friction mainly. Now therefore 2s to 3 represents the ideal constant pressure process. Ideal 2s to 3, it represents the ideal constant pressure combustion process, and 2a to 3a represents actual combustion process. So 2a to 3a it represents actual combustion process. And here you see that P3 minus P3A is equal to basically 0.07 bar. So P3, this is same as P2. So therefore P3 minus P3A, this gap is 0.07 bar. T3 is equal to 540 degrees centigrade turbine inlet temperature given. So it is 540 plus 273.15 in Kelvin, 813.15 Kelvin. And P3A is equal to P3 minus 0.07, as there is a pressure drop. So what is the value of P3? 5.05. P3 is equal to P2. So the same as P2. So it is 5.05 minus 0.07 bar, that is equal to 4.98 bar. 4.98 bar. Next, now we will be determining the mass flow rate. Now, mass flow rate is an extensive quantity, and for that, we will take help of that another extensive quantity. We will equate that with properly in appropriate equation through appropriate equation with the power, total power. This is also, you see, this is total power, not really not expressed in terms of per kg. So it is a total power. So that is also extensive property. So we will relate these quantities accordingly and try to calculate what is the mass flow rate. Now, between 1 and 2, so temperature is known. You see, between 1 and 2, the temperature here is known and the pressure ratio is given. So we know that for isentropic process, the pressure ratio and temperature ratio can be related using the isentropic process equation and the equation of state, as we know. So these are very routine calculation. So I have not demonstrated that. So you know this. So T2S by T1, you see that the pressure ratio and temperature ratio, they are proportional. So that means during the process, if the pressure is increasing, temperature also increases. So here you see that T2S by T1 is equal to P2 by P1. P2 means basically P2S here, isentropic process. So accordingly, this is RP, that is pressure ratio to the power K minus 1 by K. So here K is the isentropic index or specific ratio for the ideal gas. So T2S, here you know that T1 is known, but T2S is unknown. So we can determine T2S from this because this part is known, this is known. So we can cross multiply and determine what is the value of T2S. Simple calculation will lead to the determination of T2S. So it is RB to the power K minus 1 by K, and accordingly we will put the value of RP and K. RP is 5 and K is equal to K is equal to 1.4. Okay. Now therefore T2S is determined to be 457.17 Kelvin. Now this is from the isentropic process equation. Now we will apply the isentropic efficiency equation for the compressor, because you see that T2S is known, T1 is known, and T2A is unknown. So we can determine T2A. Although you see that during the calculation of the mass flow rate, that T2A will not be required. So this is only for the sake of completeness I have done it. Although T2A is not to be determined for the calculations that are required here, is not required. So you can use a different color for that, which is actually not required. Okay. Next, again from the isentropic process relation between 3 and 4, in the same way, you see that both are isentropic, 1 to 2 as well as 3 to 4 isentropic process. Therefore, their variations, the property variations of the property relations are similar. That means here T2 by T1, P2 by P1, they are related. Here T3 by T4, P3 by P4, P3 by P4, they are also related in the same manner. Therefore, we can determine what is T4S, because T3A is known, that is 540 degrees centigrade or 813.15 Kelvin. This is known, and this ratio is known because P3A is known, that is determined because of pressure drop, it drops. It is not 5:1, it will be something else because P3A is lowered by the friction. So it is 4.98 bar, and the denominator pressure is same as 1.01 bar. Therefore, this can be calculated, and accordingly, the isentropic temperature for the turbine exit can be calculated. So this is T4S. T4S. Okay. Next. Now again using the isentropic efficiency for the process 3A to 4, again we can determine T4A, although you see that this is also not required for this solution. So we may highlight it with a different color. This is only for the sake of completeness of the problem. We have done it. It is not needed for the problem. Since the efficiencies are given, we can directly use the ideal process and the efficiency to calculate the actual work input or work output that we will see. Now, a power, as we know that net power is equal to W dot net is equal to W dot turbine actual. That means what is the power output from the turbine in the actual process. So this is W dot T actual minus W dot C actual, that is for the compressor during the actual process, what is the work input. So this is work output and this is work input. Therefore, their sum or means algebraic sum. So it includes the minus sign. So if we algebraically add, then that will give us the net power output. So this minus this, because this is input, so it is a negative, it is having a negative sign, therefore it gives us the net power output. So the balance of the turbine work output and the compressor work output, compressor work input. So as we know that this is, the first one is m dot multiplied by Cp into the isentropic efficiency multiplied by this. So we know what is the value of work for the turbine. So that is the change in enthalpy. Therefore, this can be calculated. So it is MCP delta T, that is T3A minus T4A, T3A minus T4S. This is for the ideal process. So change in enthalpy for this process, 3A to 4S. So we can calculate the work related to that process. Similarly, so now this is the actual, therefore from the theoretical part we can determine by just multiplying with the turbine efficiency given. So this is this multiplied by this according to the definition. Now for the compressor, this is opposite, because for the compressor actual work input is equal to the theoretical work input divided by the pump compressor efficiency, the compressor isentropic efficiency. So this is in denominator. Because of that, because the definitions are altered in case of compressor and turbine. Now just putting the values we can determine. So power given as 1500 kilowatt. We have to keep in mind that we have to carefully put the values and follow the units, that means verify the units. You see that 1.04, what is the unit? Unit is kilojoule per kg Kelvin. So this is related to the property kilojoule per kg for work. So it has a unit of kilojoule per kg. It has a unit of this this has a unit of basically kilowatt. 1500, it has a unit of kilowatt, and this has a unit of kilojoule per kg Kelvin, and this has a unit of kilojoule kg per second, and accordingly this will have a unit. So this is simply Kelvin. This has a unit of Kelvin inside. Now therefore we can write after calculation of this quantity, this is coming to be 41.77. What is the unit? Unit should be kilojoule per kg. Here you see that it is Kelvin. This is Kelvin multiplied by this one. So it is kilojoule per kg Kelvin. This has a unit of kilojoule per kg Kelvin, and this is Kelvin. So Kelvin and Kelvin will cancel. Therefore, it will remain as kilojoule per kg. And in the top, we have the unit kilowatt. So the final unit of the mass flow rate will be kilowatt divided by kilojoule per kg, as kilowatt means basically kilojoule per, this will have a unit of kilojoule per kg. So therefore the mass flow rate after this division will come to be 35.91 kg per second. Okay, that is the final answer for this problem. We can determine many other quantities like isentropic, that is the efficiency of the turbine, and say work ratio, etc. These can be added to this problem. So I will suggest you that you solve the additional quantities also. But during the examination, you will be calculating only the quantities that are asked to be solved in the exam, in the question paper. But for your practice, you can solve other quantities also. Thank you.